This paper presents a technical framework for human-like motion generation with autonomous anthropomorphic redundant manipulators.
Recent findings in robotics have enabled promising opportunities in the field of human-robot interaction, for example with the development of collaborative robots in industrial settings.
But also with companion robots that can provide assistance in daily life activities. All these applications share a common important characteristic that is human likeness.
This is important since it increases the acceptability of the robot by the human and improves the predictability of the motion itself, positively affecting the safety and the effectiveness of the interaction. It is then clear that the generation of human-like movements is fundamental for the next generation of humanoid robots. State-of-the-art solutions typically rely on the optimization of arbitrary cost functions or capitalize on heavy learning methods. However, this usually comes with certain limitations such as limited motion variability and the need for very high-dimensional datasets. In this paper, we propose a new architecture that is able to overcome these limitations. To do this, we leverage on the definition of a basis of principal functions extracted from human movements. A reduced number of these functions is then enrolled in a planning problem.
We defined an incremental procedure that enrolls the minimum number of these functions tailored on the degree of movement complexity required for the specific task.
And finally, we defined a procedure to map the obtained trajectories on a generic redundant manipulator. Looking at humans, we observe a significantly high complexity, with more than 50 independent muscles used to move the upper limb. Yet, the effort required at the neural level to control such complexity seems negligible. So the typical question is, how can the brain cope with the abundance of our body? And this, in robotic terms, become, how can I simplify the problem of motor control to provide design guidelines for robots? We then need a tool to reduce the functional dimensionality of the movements. To this goal, we used functional principal components.
This can be regarded as a functional extension of principal component analysis. Each functional principal component will be a time vector, and a combination of a sufficient number of functional components can reconstruct all the movements. To do this, we performed an experimental campaign to collect kinematic data of human upper limb movements.
We considered here a selection of 30 activities of daily living, and the motion of the arm was recorded through a motion tracking system. These tasks were selected in order to span most of the upper limb range of motion and to include the main entries of the grasp taxonomy. Marker movements were then mapped on a 7 degrees of freedom model. Please refer to the paper below for additional details. And then we come to the functional analysis. The idea is to identify the first functional principal component as the function that minimizes its distance with respect to the entries of the dataset. Then we can define a second functional principal component that again minimizes its distance with respect to the entries of the dataset, with the additional constraint that this is orthogonal to the first one.
And so on with all the other components.
In our dataset, a very reduced number of functional principal components, defined as modulants of a mean trajectory, can explain most of the variability. This definition introduces a hierarchy between the functional principal components in terms of the importance in the reconstruction of the dataset. We can then use this basis of functions in a planning problem to generate an arbitrary motion.
Here we have the formalization of the planning problem. The goal is to minimize the error between the desired initial and final joint posture and the actual movement. The trajectory is constrained to be a combination of a static configuration Q signed plus the time series as 0, which is defined as the average trajectory of the recorded dataset, and a combination of functional principal components that are named here as E. These functional principal components are enrolled with a coefficient alpha that is free to vary in our optimization. Note that these quantities are defined at the joint level. This problem here has a solution in closest form that is reported below. The fact that we don't need to optimize for the generation of point-to-point motion gives the opportunity to include other characteristics such as the obstacle avoidance. We extended our implementation to the obstacle avoidance case by including a second term to the cost function. The role of this second term is to maximize the distance between the whole robot during the movement and the obstacles. A recursive numerical routine has been implemented to solve this optimization problem. At the first iteration, a solution is searched with m equal to 1. In case the solution does not reduce the error below a desired threshold, the procedure is repeated by increasing the value of m, until the problem is solved with the desired accuracy. We performed multiple tests to evaluate the quality of the planned trajectories, evaluated in terms of bell-shapedness of the velocity profiles and jerk values. We show here 4 examples tested with and without obstacles on the end effector or on the elbow trajectory. Our algorithm provides movements planned in joint space. A mapping problem needs then to be solved to implement this on a generic redundant manipulator. This is performed in this paper through a Cartesian impedance control. The torques provided to the robot will include a term that compensates the dynamics of the robot, then its inertia, corollary, and gravity contributions. And then we will have a term that minimizes the error and its derivatives between the actual robot end effector and the endpoint of the 7DOF's model we used to plan the movement. To deal with the redundancy, we used a second controller at the elbow level. The goal of this second Cartesian impedance controller is to minimize the distance between the elbow of the robot and the planned motion at the elbow level. To keep the effects of the control uncoupled, we project the second controller in the null space of the first one. And here we show an example of a typical reach-to-grasp movement in which the robot needs to move toward the left side of the table. The movement is mapped on the robot with a good accuracy and preserves the characteristic bell shape of the velocity profile during the motion. In all our tests, although some oscillation are introduced by the robot, the jerk values are always below 10 to minus 2. Here instead we have a case of self-feeding when the robot is drinking from a bottle. Also in this case, the movement is mapped with a very good accuracy and preserves low values in the jerk profiles. In this video, we demonstrated the potential of a new algorithm for human-like motion generation of a generic redundant manipulator. We are now working to extend this approach also to the definition of impedance parameters. Thanks very much for watching. Please contact us for any question.